Open Science Physics, College Physics, Chapter 7, problem number 63. It has to do with this ball launcher, but you know what? I have a ball launcher. So let's just do this, just to start, right? So I have a ball. I don't even know the mass. Doesn't really matter. We'll use the numbers in the value in the problem right there. And this is a pretty, I've gone through many different ball launchers. This one's from, it's Pasco, right? Yeah, this is a Pasco one. They've really improved a lot over the years. So you put the ball in here. There is a spring, but we can pull the spring back by pushing this down until it clicks. And we've compressed the spring. Okay, now I can launch it. They have a little launch trigger right here. I'm going to launch it right here. Let's see. I don't think it goes too high at the setting. And I caught it. So that's like bonus points for me for catching it. But that's the problem that we're going to do. We want to find a couple things. They give us the spring constant, 300 newtons per meter. The mass of the ball, they say 10 grams. It's compressed 7 centimeters, which this is probably around that. It's around that. Then they want to know, first question is, what's the force needed to compress the spring, which I don't like. There's a couple parts of this problem I don't like, but I'm going to do the whole thing anyway, because that's how I like to do things. So I'm going to put this down over here. And let's get started. This is a multifaceted problem, and I love that, because it's kind of real world in that it doesn't say, this is, use the work energy principle. It just says, just figure it out, right? And that's the way real life is. Real life isn't categorized by section 3.28 or whatever. But enough of that. Where's my chalk? Here's my chalk. Okay, so the first question, it literally said, and let me read this to you because I didn't really like it. It said, how much force is needed to compress the spring? And I don't like that question. Because remember that we have this F is KS. So this is the force due to a spring. That's the spring constant, the stiffness of the spring, and that's the amount that's compressed. So the more you compress it, the greater that force. There's not a constant force that you need to compress it, although it seems to be saying that. I guess they want the maximum. I mean, they must want the maximum, right? That's what we're going to find. Okay, so it's not too hard. If I have my spring, I know the compression, I know the spring constant, it's just plug in there. And I don't even know why we would do this. So we have 300 newtons per meter times the compression. That's in newtons per meter, so I need that in meters. So that's 0.07. Let's just calculate that. So on, drop, 300, enter, 0.07 times. I get 21 newtons. Okay, so that's part A. 21 newtons. See, we're making progress though. And I do want to point out the stuff that I did before I started the video and before I shot the ball. And that's, I drew a picture, right? And you may think, that's dumb. I don't need a picture. I can do it without the picture. But the picture really helps us. The picture helps us kind of process the question and see what they're given and stuff like that. And I draw the spring and the compression amount. I have up here, I know the ball is going to get shot up. I'm going to want to find that height. And then I wrote down all the values I need. And it is important here to put units. The mass of 10 grams. I'm going to need that in kilograms, but 10's the mass in grams. The spring constant in newtons per meter. And then I wrote down all the things that I'm going to need, which you wouldn't do at the beginning anyway. But I don't want to have to look back at the problem. So let's proceed. The next question has another issue with it. It says, I'm going to literally read it to you. To what maximum height can the ball be shot? Now, it's not going to make a huge difference, but the question is maximum height from where the ball started or from the end of the gun, right? The launcher. So here's my launcher. If I start right here or start right there, there's going to be a difference of 7 centimeters. So I'm going to start from here. I don't know why. Okay, so this is a work energy problem because of height, right? If it said how long is it in the air, if you think time, think Newton's second law. If you think how high, how far, distances, think work energy. So the work energy principle, just to review, I can erase this. The work energy principle says that the work is the change in the energy. and we need to pick our system. I make a big deal of picking the system, okay, even though it's not even mentioned in the book. Because depending on what you choose for the system tells you what things do work and what things have energy. It tells you what kind of energies you have. And so I'm going to pick, for my system, 3 things. I'm going to pick the ball. I mean, that seems obvious. I'm going to pick the earth. That might not seem obvious. And I'm going to pick the spring. By picking the earth is going to exert a gravitational force on the ball as it moves up. So you would have to calculate the work done by gravity. Unless there is part of your system, then that work is an internal force, and we don't have work done by gravity. And instead, we'll have our types of energy, gravitational potential energy. UG is mgy. Now, since we have the ball in there, we're going to have, it's going to be moving. We could have kinetic energy, 1/2 mv squared. And then because we have that spring in there, we have a spring can be compressed or stretched, and it can store energy, and that's U. I'm using U for potential energies. It's 1/2 k s squared. That's a spring constant, and that's the amount it's stretched or compressed. So that tells us the kind of energy that we have, and it also tells us what does work. What's doing work on my system of the ball plus the earth plus the spring? Nothing, right? So now I have the following. Work is the change in kinetic energy plus the change in gravitational potential plus the change in spring potential energy. And I need to pick my 2 locations, right? Initial position, final position. Initial kinetic energy, final kinetic energy. So I'm going to pick this as position 1 and that as position 2. And then we'll talk about other options that you could do instead after that. So I'm going to erase this. No. So let's just write this as 0 K2 minus K1 plus UG2 minus UG1 plus US2 minus US1. So the change in kinetic energy, change in gravitational potential energy, change in spring potential energy. Now let's look at our 2 points, point 1, point 2. What do I know about the kinetic energy at those 2 points? Well, when I launch the ball, right when I launch it, the velocity is 0. At the highest point, the velocity is 0. So my K2 is 0. My K1 is 0. Now let's think about the gravitational potential energy. It has this value of y in there. Now, we're really doing a change of potential, so it doesn't really matter where we pick, where we measure our y from. We can pick wherever we want. I'm going to pick, that just makes sense, right? I'm going to pick y is 0 at the beginning. That's just going to make our lives easier. But trust me, anywhere that you pick will work, and you will get the same value. If that's the case, then my initial potential, mgy, would be mg0, so it would be 0, so this is 0. That is not 0, though. Okay, now what about the spring potential energy? This has that S in there, how much it's stretched or compressed. So let's just look at our 2 positions and see if we can say anything about the spring potential energy. Right here, the spring is compressed at a distance of 7 centimeters. When the ball's up here, how much is the spring compressed? If you say it's compressed or stretched the height, that would be true if the ball was stuck to the spring and it was launched up. But it leaves it. When it leaves it, the spring just goes back up to the unstretched position. So in position 2, S is 0. It's not stretched or compressed. So that means that this is 0. Okay, so now we have a much simpler equation. I don't really have much in there at all, right? 0, 0, 0, 0. I only have 2 non-zero values. That's a win for us. Okay, let's go ahead and start putting in some stuff. I have 0, 0, 0. UG2 is going to be MGH. I don't know what that is. I don't know how high that is. And that's measured from the initial position of the ball. And then I have minus, I have 0, 0 minus 1/2 k s squared. and I want to solve for h. I'm going to add that to both sides. I get mgh equals 1/2 k s squared, and I need to divide both sides by mg. H is k s squared over, what's it, k, 2gh. Let's put in our values. 300, 0.07 squared to 9.8, what, m, 9.8, and then the mass was 10 grams, so I divide that by 1,000, I get 0.0, that's 100, 0.1, is that right? 10, sometimes you just space out. So 10 divided by 1,000, I don't know why, it's okay to space out. 10, enter 1,000 divided by, yeah, I was right. Okay. Whew. Okay, let's put this in our calculator. But I'm actually going to put it in my calculator, not our calculator. 300.07 squared times 2 divided by 9.8 divided by 0.01 divided by, and I get 7.5. meters. That's pretty high, actually. Okay. Now, I do want to point out that if you measure from the top of the launcher instead of the initial position of the ball, I'd have to subtract 0.07. But it's pretty close. What? That's 7.43. So it's still pretty close. And that's fine. So I'm going to put over here height of 7.5. Okay. Now, the next question is also problematic. I'm going to read it to you. Oh, no, I did tell you. Well, if you wanted to break this up into 3 pieces, and this is a common strategy that I see students do this. Okay, look, I can go from 1 to 2 to 3. And then I'm going to, from 1 to 2, I'm going to calculate the change in energy. I'm going to find the speed right here, the velocity. And then now I can say it has velocity and it has kinetic energy and it's moving up there. You could do that if you want, but I don't need that intermediate step. I don't need to know the velocity except for the next part. Okay. And we're going to make some assumptions for the next part too. So let me just get to let me read the second part. Part C. At what angles above the horizontal may a child aim to hit a target 3 meters away as the same height? This is problematic. Okay, so here's my picture. There's my launcher with my spring, and it's compressed an amount, and it's angled at theta, and it's going to go like this. And this is, we'll call this x equals 3 meters. Yeah, because now we have a projectile motion problem. But in projectile motion, we need to find the launch velocity, v0. Now, I'm going to be honest with you. Let me get my launcher, because I think this is an important demo. Imagine that I compress this, and then I launch it. And then I catch it, because, yeah. And I calculate the launch speed as it leaves the cannon, the launcher. Okay, and I can do that. We essentially did that. If I just went to here, I could do that. Now imagine that I do the same thing. I push it back, and I launch it horizontally. It's going to go faster. It's not going a lot faster, but when I launch it up, I have this change in gravitational potential energy going from here to there. And when I launch it horizontally, I do not. So the launch velocity depends on the angle. Technically. I don't think they intended you to take that into consideration because it makes the problem significantly more difficult. So we're not going to do that. So instead, we're going to just assume that the ball goes from here to there and the change in gravitational potential energy is small. We can use that to calculate our velocity. And then we can solve for our angle here. So let's calculate our launch velocity. I'm going to choose the system a little bit different. It's just going to be the ball plus the spring. And so here's my position 1, there's my position 2. And I'm not going to worry about changing gravitational potential energy. So in that case, the work done is 0, and that's going to be the change in kinetic plus change in spring potential energy. So I have 1/2 mv2 squared minus 0, the initial velocity is 0, plus 0, right? Then there's right here the final spring potential energy is 0 minus 1/2 ks squared. So I can use that to find v2, which is my v0 in the projectile motion problem. You see how that works? Okay, so let's get v0. Well, I'm switching. I'll call it v2 still. v2 squared is going to be equal to the 1/2s cancel. I get ks squared over m. Now let's put in our values. v2 is going to be the square root of 300 times 0.07 squared over 0.01. And that's my launch velocity. Drop. 300, enter. 0.07 squared times 0.01 divided by square root. I get 12.1. So V0, I'll put it right here, 12.1 meters per second. Okay, and that, again, that assumes there's no change in gravitational potential energy, but there would be. Now we have a projectile motion problem. Don't you remember projectile motion? So for projectile motion, it's going to go, I'm going to start here at x equals 0, and I want to find right there, I know the final position. So in the x motion, I know the following. I know x final is x initial plus v0 cosine theta t. Right? This is going to be my x velocity. That's the angle theta. So that's cosine theta. I don't know t. I know x. I know v0. I don't know theta. Okay. I know this. I know that. I know that. I know that. I don't know theta or t. I'm trying to find theta. So let's go to the y motion. In the y direction, I have y is y0 plus v0 sine theta t minus 1/2 g t squared. Now again, I don't know theta and I don't know t. So what I can do is to solve, I'm going to solve this for t and then plug it in there and then solve for theta. And you could do it the other way, but I got a weirder t over there. So I'm going to delete this, which also is known as erase. And I'm going to solve this. Let's put in 3 v0 cosine theta t. And yeah, I do know v0, but I'm just going to leave it like that. So let's solve this for t. I get t equals 3. I'm going to put that as x. X over v0 cosine theta. Now if I plug that in up here, I get the final y and the initial y are both 0. That's a little bit nicer. So 0 equals v0 sine theta times t, which is this, x over v0 cosine theta. And then I have minus 1/2 g, and then I have to square this, which is going to be x squared over v0 squared cosine squared. Okay, so I need to solve that. Let's add this to both sides, and I get 1/2 g x squared over v0 squared cosine squared theta equals sine theta x over cosine theta. That's it. This x cancels with one of those. This cosine theta cancels with one of those. So let's multiply both sides by cosine theta, and we're going to have to do a trick here. And I hate tricks, but I just realized we're going to have to do a trick. So if I do that, I get cosine theta sine theta is equal to gx, because it's squared, over 2 v0 squared. And we want to solve for theta. Now, let's just check, right? Because this should have no units, so this should have no units. G is in meters per second squared times meters gives me meters squared per second squared, and then V0 squared is meters squared per second squared, so that's good. So I don't remember that trick. Let's see, cosine times sine is equal to what? I can't remember that. The basic trig. You can forget stuff, right? Trig cheat sheet. I'm looking it up. Formulas and identities. Okay, here it is. Sine, oh, crud. I'm not going to solve this problem because it says sine, oh, that's sine alpha. Okay. Oh. Here's my trig identity. Cosine, I'm writing it down. Cosine alpha sine beta is 1/2. I'm not going to back down. I'm not backing down. It's 1/2 sine of alpha plus beta minus sine of alpha minus beta. But in this case, beta and alpha are the same, right? Because we have a double. So cosine theta, sine theta is going to be sine 1/2 sine of 2 theta. So this is 1/2 sine of 2 theta. We could derive trig identities until we get, blue in the face, but it's all fine. So now the 1/2s cancel. I get sine 2 theta equals gx over v0 squared, and 2 theta is the inverse sine of gx over v0 squared. Theta is 1/2 sine inverse gx over v0 squared. Let's plug our numbers in. 1/2 is 1/2. Inverse sine of 9.8 times 3 divided by my velocity 12.1, 12.1 squared. Okay, we got some calculator stuff to do here. And again, you need to be like friends with your calculator because it's not trivial to enter that in. I'm going to do it my way, but I use this RPN notation because I use Hewlett-Packard calculator, which I like a lot. So I'm going to enter all this stuff first, take the inverse sine, and then divide by 2. So I'm going to start right there with the 9.8. 9.8, enter 3 times 12.1 squared. I can never see the squared. Squared divided by. Now I'm going to take the inverse sine. And my calculator is in degrees mode. So I get 11.5. And now I'm going to divide by 2. Seems like that's too small, but I get 5.7. That seems really small, 5.8 degrees. Okay, now the last part said, what's the range? I'm not going to rederive the range equation, but the range is when you're going to get the maximum range when theta is 45. I'm not even going to do it, but I should do it just to check and see if it's way bigger than this. Because that just seems so small. Let's see, 9.8 gx over v. Let me just double check that. I am in degrees, right? Okay, I am. So 9.8, 3 times 12.1 squared divided by inverse sine. Okay. I'm going to stop there because it's a long enough problem, and it's really about the work energy part. I was just trying to fulfill that part of the question because that's what they had in the book, and it is fun, right? It's fun, but okay.